We are living in an era where we can go to space and then come back. We can even stay there for some time. But have you ever wondered how we came to know that it's possible? And more importantly, why are we able to walk, run, jump, and do pretty much everything without falling into the earth? This is due to one of the four fundamental forces of nature, gravity. In this series, we explore the wonders of our planet and the forces that make life possible. From the Earth's core to its atmosphere, we'll uncover what makes our home so unique. In today's episode, we will discuss the force that binds the cosmos together and keeps us grounded: gravity. If someone asks you what keeps us from floating away into outer space, you might say, well, it's common sense, isn't it? It's because we're on Earth. We live on a solid ground. And if we were anywhere else, we would float away. Well, not exactly. See, we don't actually stick to the Earth. We just appear to be sticking to it. Let me ask you another question. What keeps the moon in orbit around the Earth, or the Earth revolving around the sun? Because the moon and the Earth are 384,400 kilometers apart. There must be something keeping them bound. Enter gravity. Gravity is a force of attraction between any two objects that have mass. The more massive an object is, the stronger its gravitational pull. So it's not just the Earth that has a gravitational pull. Every object does. You could argue that if we were anywhere else, like near a black hole, we would get pulled towards it instead of the Earth. Well, yes, that's true. But we are not anywhere else. We are right here on good old Earth. And while there may be some anomalies due to other celestial bodies like the moon, which causes tides on our planet, we are largely unaffected by anything else. We are simply too small and weak to be affected by anything else. Or are we? If you've ever wondered why you feel heavier on Earth than on the moon, it's because of gravity. Gravity depends on two things: the mass of the objects and the distance between them. The more massive an object is, the stronger its gravitational pull, and the closer the objects are to each other, the stronger the gravitational force between them. So when you stand on the surface of the Earth, you're feeling the gravitational force between you and the Earth. The Earth is much more massive than you, so its gravitational pull is stronger than yours. As a result, you feel heavy on the Earth. But when you're on the moon, you're much farther away from the Earth, so its gravitational pull is weaker. At the same time, you're closer to the moon, so you feel its gravitational pull more strongly. The combined effect is that you feel lighter on the moon than on the Earth. You may think that the force of gravity is the same everywhere on the Earth, but it's not. It actually decreases with altitude. That's why it's easier to fly a plane at higher altitudes. When you're higher up, you're farther away from the center of the Earth. So the gravitational force between you and the Earth is weaker. Now, what happens when an object gets too close to a black hole? You might think that once you cross a certain point, called the event horizon, nothing can escape the black hole, not even light. But that's not entirely true. You see, the thing about black holes is that they're incredibly dense. They pack a lot of mass into a very small space. That means their gravitational pull is incredibly strong. If you get too close to a black hole, you'll be pulled in and crushed to death. But if you don't get too close, you can actually orbit a black hole. Just ask NASA's Parker Solar Probe. It's been orbiting the Sun for the past 5 years. When we talk about gravity, we usually assume that it's a force that pulls objects towards the center of the Earth. But that's not strictly true either. Gravity is actually a force that brings objects together. It doesn't matter if they're made of matter or antimatter. If you take two objects and bring them close enough together, they will attract each other gravitationally. Now, what happens if you take two objects made of antimatter and bring them close enough together? Well, since antimatter is attracted to regular matter by the force of gravity, it'll pull the regular matter towards it. And since the regular matter is attracted to the antimatter by the same force, they'll keep falling towards each other until they collide and annihilate each other. The result? A big explosion. So even though we can't see gravity, we know it's there because we see its effects all around us. Planets orbit stars, galaxies orbit each other, and most importantly, we stay on the ground because of it. Gravity is one of the fundamental forces of nature. It's one of the 4 forces that govern the behavior of the universe. The other 3 forces are the electromagnetic force, the strong nuclear force, and the weak nuclear force. The electromagnetic force is what causes electricity and magnetism. The strong nuclear force is what holds the nucleus of an atom together, and the weak nuclear force is responsible for certain types of radioactive decay. Of these 4 forces, gravity is the weakest. But it's also the one that acts over the longest distances. Now, you might think that the force of gravity is constant, but that's not true. In fact, it's constantly changing. For example, if you weigh yourself on a spring scale, you'll notice that your weight changes depending on how hard you pull on the scale. The harder you pull, the less your weight. That's because you're actually stretching the spring, which makes the gravitational force between you and the Earth weaker, and you can actually use this to your advantage. If you want to make yourself feel heavier, just find a way to increase the gravitational force between you and the Earth. One way to do this is to increase your mass, but there's another way to You can decrease the distance between you and the Earth, and you do that by jumping. When you jump, you're actually bringing yourself closer to the Earth, and that makes the gravitational force between you and the Earth stronger, which makes you feel heavier. Of course, you don't actually become heavier. You're still the same mass that you were before. It's just that the gravitational force between you and the Earth has changed. Now, this is all just theory, but I believe that if you could find a way to decrease the distance between any 2 objects with masses, you could actually increase the gravitational force between them to infinite strength. This would create a black hole. It's important to understand that gravity is not a force that only affects objects with mass. It also affects massless particles like photons. In fact, gravity affects everything except for one thing: Time. Time is the only thing that we know of that is not affected by gravity. Now, this raises an interesting question. Why does time pass more slowly on Earth than it does on the Moon? Well, remember that the force of gravity depends on the mass of the objects and the distance between them. The Earth is more massive than the Moon, so its gravitational pull is stronger. That means that time passes more slowly on Earth than it does on the Moon. This is known as gravitational time dilation. Now, this effect is very small. On Earth, time passes only about 1 second slower than it does on the Moon, but it's still measurable with very precise clocks. So if you want to live longer, you know where to go. But let's not forget that gravity also plays a crucial role in our everyday lives. It's what keeps us from floating away into space. It's what causes the tides in our oceans. It's what makes it possible for airplanes to fly. Gravity is a force that we often take for granted, but it's one of the most important forces in our lives. And I think it's important that we understand and appreciate this force of nature that keeps us grounded, quite literally. Thank you for watching this episode of Gravitas Plus. I hope you enjoyed it. If you did, please leave a comment below and tell me what you want to see in the next episode. And don't forget to subscribe for more episodes.